Start with a question for you to ask yourself. Without overthinking it, assume that you put some drug on a cell and you added enough drug that 50% of the receptors had drug bound to it. What percent maximal response would you expect? Now, the obvious answer here is that if you bind 50% of the receptors, you would expect that you would get 50% response. Because it would seem like if you bind 0 receptors, you're going to have 0 response, and that in order to achieve 100% response, you're going to have to bind 100% of the receptors, and so you just assume a linear response, and so 50% gives 50%, right? And so that idea of the proportionality between binding and response is called occupancy theory. It's called occupancy theory because the idea is that in order to get a response, the receptor has to be occupied by the drug. And so the very basic idea of occupancy theory is that the response is proportional to the number of receptors that are occupied. And so, like we just said, in order to get 100% response, you're going to have to occupy all of the receptors. Now, we have a way to calculate occupancy. So this is the Langmuir equation. At the top of my head, I don't remember if we covered this in the fundamentals course. I'm pretty sure we did not. So I think this is new to you. This is the Langmuir equation. And so it looks complicated, okay? I want you to focus on this top one. Ignore the bottom one. This is just another way that people like to write it. I put it in there in case you see it someplace else. You can realize that this is the Langmuir equation. In the Langmuir equation, RT here is the total number of receptors. DR is the drug receptor complex. So if you take the number of drug receptor complexes and divide by the total number of receptors in the system, all you're doing is you're calculating the fraction of receptors that have drug with them, the part divided by the whole. That's all this is. So it's a complex divided by the total number of receptors gives us lowercase r. And this lowercase r is going to be occupancy. Now we can mathematically predict what this is going to be using the Langmuir equation. And the Langmuir equation is drug concentration, that's our D here, or agonist concentration on the bottom, divided by drug concentration plus KD. And if we graph the Langmuir equation with increasing drug concentration on the x-axis and then occupancy on the y-axis, we see this curve that comes up and approaches a maximum at 1, because we can't have more than an occupancy of 1. 1 occupancy is 100% occupancy. This is because we're in fractional mode here. And so the KD is the concentration of a drug that causes 50% occupancy. And that is a definition. You can go both ways. You can say, well, I need to find the KD, and so let me find the drug concentration that gives me 50% occupancy. Or you can say, well, I know the KD of this drug is X. And so X must be, at concentration X, we must have 50% occupancy. And we max out at 1 because at this point, our numerator, our DR, is approaching the same as our total number of receptors. So you need to remember the Langmuir equation. This is a very important equation in pharmacology, so you need to remember it. So we said that according to occupancy theory, there was a 1-to-1 or proportional relationship between occupancy and response. In order for that to happen, we're going to use this simple model here at the top of our slide. A here is our agonist, or think of it as D for drug. When it comes together with a receptor, it forms an agonist receptor complex, and when that complex forms, it gives a response. And here, we're assuming a 1-to-1 ratio between the binding, the occupancy, and the response. In our graph here, again, this is actually the Langmuir equation. And so, yes, it looks very different than this equation, but the difference is the scale on the x-axis. Here we have a linear scale, and here we have a log scale. A lot of times, we will graph the Langmuir equation on a log scale so that we get this sigmoid curve, this S-shaped curve. In this situation, KD is again where we get 50% occupancy on the y-axis, but it's also the inflection point of this curve. You see, before the KD, the graph gets steeper and steeper, and then after the KD, the graph gets shallower and shallower. Now, the Langmuir equation, assuming 100% or a pure relationship between occupancy and response, a response curve showing percent response as a function of agonist concentration would be exactly the same as our binding curve. And so when you look at this graph, imagine that the dotted line is right on top of the solid line. They just couldn't draw it like that because if you put a dotted line on top of a solid line, you can't see the dotted line. And so they had to put it right next to it. So in this situation, the KD, 50% occupancy, is the exact same concentration as the EC50, the effective concentration 50, the concentration that gives us 50% maximal response. And this is just showing over here the relationship. So AR divided by RT was our occupancy. And here we just have the actual constant effect divided by the maximal effect. And so we're just showing that, assuming this 1-to-1 relationship, these are actually identical mathematically. And so I am going to give you a question here, and I'm going to just pause a second. I suggest when I finish presenting this question that you pause the video, answer the question, and then come back to see the answer and move on. So in this situation, we have a person that is smoking one cigarette. And this person is 100 kilograms in mass. And I give you some information. I say that in that one cigarette, that person is going to absorb 1 milligram of nicotine, and that the molecular weight of nicotine is 162 grams per mole, or atomic mass units, or Daltons, or whatever unit you want to put on it. It's all the same. I give you the KD of nicotine, that is 12 nanomolar. And I tell you that the volume of distribution is 3 liters per kilogram. You may have to look up how to convert 3 liters per kilogram into volume of just the actual volume of distribution. You're going to have to use the fact that the person is 100 kilograms. Now, I'll give you a couple warnings. Note that nicotine has a KD of 12 nanomolar. Don't forget what nanomolar means. Nanomolar is 10 to the negative 9th molar. You're going to have to use the Langmuir equation here and make sure that your KD and your drug concentration are in the same unit. Also, you're going to have to calculate drug concentration, which is not given to you. You're given a mass of drug, 1 milligram, and then you're going to have to calculate the volume that is dissolved in, and you're going to have to use that to calculate the molarity of the drug. Okay, so that should be all the information you need to do this. You may have to brush up on some basic chemistry in calculating molarity, but when you think you have an answer, come on back. Okay, so I am going to assume that you now have the correct answer. The correct answer is hopefully 63%. Now, how do we get that? So I said Langmuir equation, right? And so right now we're assuming that if you calculate occupancy using the Langmuir equation, that occupancy is going to be exactly the same as the percent maximal response. And so in reality here, all you have to do is calculate occupancy. And so you have to calculate D divided by D plus KD. Now, to get drug concentration, you had to convert 1 milligram of nicotine into moles of nicotine, and then you had to divide by volume, because molarity equals moles divided by liters. Volume of distribution is 3 liters per kilogram, is 100 kilograms, and so the volume of distribution here is 300 liters. Take the moles of nicotine that you calculated, divided by 300, that's your drug concentration. In molarity, convert 12 nanomolar KD into molar, and so it's just 12 times 10 to the negative 9th molar. Plug it into the Langmuir equation, and you get 0.63, or 63%. But unfortunately, it is not that simple. There is not usually a one-to-one relationship between occupancy and response. Here, we're looking at the response of a rat aorta to a number of different agonists. So on the x-axis, as we go to the right, we're just increasing the amount of agonist. And on the y-axis, we have response. Now, I'm going to tell you that each of these drugs achieves 100% occupancy at a high enough concentration. And so all of these drugs, when they plateau, they're at 100% occupancy. But notice that the percent response is very, very different between them. And so this tolazoline, even at 100% occupancy, achieves maybe 10% response. And so there cannot possibly be a one-to-one relationship, and it must be more complicated than that. In order to help describe this and allow us to do calculations with it, we're going to introduce a new variable. This is alpha, or intrinsic activity. It can also be called intrinsic efficacy. These are the same exact thing, just different words. This is a multiplication factor that links our occupancy to our effect. It reflects the ability of a drug or an agonist to produce a stimulus once it is bound. So here we have capital E for effect. This is going to be the same thing as response. Effect and response are the same thing. So before, we said that effect or response was equal to occupancy. Now we've just added a multiplication factor here. If alpha is 1, then E does in fact equal R, and we call this a full agonist because it has the 100% ability to convert a binding event, occupancy, into an effect. If alpha is between 0 and 1, we call that a partial agonist because occupancy does cause effect, but it's not 100% efficient in converting occupancy into effect. If alpha is 0, it is an antagonist because at that point it is binding. It is causing occupancy, but no matter what the occupancy is, R, we're going to multiply it by 0, and so effect is 0. And that is what an antagonist is. That's what it does. It binds to a receptor, and then after binding to that receptor does not cause an effect. Now, we haven't talked about something called an inverse agonist yet. That's coming up. But an inverse agonist would have alpha as a negative number. Now, that's not going to make sense yet, okay? Just keep that in the back of your mind when we talk about inverse agonists in a later lecture. So now we're going to revisit this question. This is the same exact question. You don't need to redo all of the math. Remember, the correct answer for the first time around was 63%. Now, all we've done is we've added the fact that alpha equals 0.77. Use that fact to calculate the new maximal response in this situation. Okay, so I'm going to assume that you paused it, you did the math, and you got 49%. All this was 69 or 63% times 0.77. And so remember, the equation is E equals alpha R, R was 0.63 from the previous question. Multiply it by alpha, which was 0.77, and you get 49%. Now I'm going to ask you another question. Imagine we have a cell, and in that cell, we have 10 receptors. You add some agonist to it, it doesn't matter what the agonist is or how much you added, and you get a response of 8. Now, there's no unit on that, just you get a response of 8. Now imagine we have next door, we have a cell that has 100 receptors on it, and we add the same amount of drug, or same amount of agonist. So the occupancy in both cells is going to be the same, but this one has 100 receptors, so 10 times more receptors, which means that if the occupancy rate is the same between them, the one with 10 times more receptors will have 10 times more receptors occupied. And so taking that into consideration, what do you expect the response to be in the cell that has 100 receptors? You expect it to be 8, the same as in the cell that had 10. You expect it to be 80, 10 times the response that you had in the cell that had 8 or had 10 receptors, or can we not tell? Now, there's no math to do here, so we're just going to move on. And the correct answer here is it's impossible to tell. And remember, this is science. And not only is it science, it's basically biology. Chemistry and physics have hard answers. They have laws. This does that. But in biology, we don't have laws, right? Everything is complicated. Everything, even when you think you've got it sorted out, you actually don't really. And so the easy answer is it's impossible to tell. But why is that? So before we looked at this process here, where the agonist bound to a receptor to make an agonist-receptor complex. But usually, the response or the effect that we're measuring is not the immediate result of that agonist binding to a receptor. That agonist binding to a receptor causes a stimulus that then causes A to happen, which causes B to happen, which causes C to happen, which causes D to happen, and what we're actually measuring is D. And so there's a lot of things happening between the agonist binding to the receptor and what we are measuring. We're going to call this the cellular cascade, the stimulus response cascade, anything like that. The cellular machinery that is responsible for converting the binding event to a response. In some situations, this may have low efficiency, causing a low response. In other situations, it may have a magnifying effect, taking a small stimulus and creating a large response. So because of that, we're going to have to change our equation again. So now, our response, capital R, equals F times alpha times lowercase r, which is still occupancy, times RT, which is still the total number of receptors. Now, if you remember from math, remember that these being in parentheses don't actually change this equation. The equation would be exactly the same if I said F times alpha times R times RT. The only reason these parentheses are here is to conceptually show that this happens with the agonist and receptor, and the F is the stimulus response mechanism, which is a separate process. And so what we're doing in this equation is we're taking occupancy, multiplying it by the total number of receptors. So this is a fraction. If we multiply that fraction by the total number of receptors, what we're doing is we're calculating the actual number of occupied receptors. We then multiply that by our intrinsic activity to get how many receptors actually had an effect. And then we take that and we multiply it by F. Think of F for fudge factor. This incorporates all of the things that happen in that cell. There's no way that you can predict F. You have to do experiments and just calculate what F is based off evidence and data. And so it's a fudge factor. It's a number made up in order to make this match your measured response. And so F and RT are actually based on the tissue that we are working on. The tissue that we're working on, if we change, we're going to have a different F and we're going to have a different number of receptors. However, the KD, which helps determine occupancy based on the linear equation, and alpha are based on the drug that we are using. Now, we're going to see how this causes a change in our graph. So remember before, the first time we saw a occupancy curve on top of our response curve, they were literally on top of each other. But now we know that there isn't a one-to-one relationship between them. And so here in the top right corner, we have our occupancy curve. But we take the results of that and we put it into a new function. This function shows us the relationship between a stimulus coming from occupancy and converts it into response. Now notice that a very small stimulus causes a very large response. There's an amplification process going on here. And so that causes our response curve to be shifted to the left. And if we shift to the left, we are shifting to lower concentrations. So if we put the stimulus or the occupancy and the response curves on one graph, we see that they are no longer on top of each other. The response curve is shifted to the left, to lower concentrations. So now the EC50 is lower than the Ka or the Kd. And so we get a larger response at lower concentrations than we do with binding. So I am going to stop here for this video, and I'm going to pick up on the next video on the next slide.